Before we begin, please note that the information in this presentation is for educational and informational purposes only. It is not intended to be a substitute for professional financial, investment, or career advice. The views and opinions expressed are based on publicly available information and case studies, and you should always conduct your own research and consult with qualified professionals before making any decisions. Imagine you're on a warship, a United States Navy destroyer, 3,000 miles from the nearest friendly port, slicing through hostile waters. Suddenly, an alarm blares. A critical valve in the engine room has cracked. It's a small piece of metal, no bigger than your fist, but without it, the ship is dead in the water. A sitting duck. 100 years ago, this was a mission-ending, potentially life-threatening disaster. The captain's only option would be to radio for help and pray. The replacement part, if one even exists in a nearby warehouse, would have to be flown out on a specialized aircraft, dropped by parachute and hopefully recovered. A process that takes days, maybe weeks. All while the ship and its crew are exposed. But on this ship today the response is different. The captain doesn't panic. Instead, an engineering officer walks over to a computer, pulls up a digital blueprint of the broken valve, and hits send. In a nearby compartment, a machine hums to life. It's not a welder, it's not a lathe. It's a 3D printer. A specialized laser begins dancing across a bed of fine metal powder, fusing it together, layer by microscopic layer. Within hours, an exact replica of the broken part, forged from high-strength steel, is ready. It's installed, the engine roars back to life, and the mission continues. This isn't science fiction. This is happening right now aboard vessels in the US Navy. Now, what if I told you that same technology, that same incredible power to create exactly what you need precisely when you need it, is about to do for the American factory what it's doing for that warship? What if this is the key to finally stopping the bleed of jobs overseas? The key to rebuilding our manufacturing base, securing our nation from crumbling supply chains, and launching a new American industrial revolution for the 21st century? Because that is exactly what's happening. We are on the verge of the single biggest shift in how we make things since Henry Ford invented the assembly line. And unlike past revolutions that sent jobs away, this one is bringing them home. Think back. Just a few years ago, remember walking into a supermarket and seeing empty shelves where toilet paper used to be? Remember the global panic over a shortage of simple paper masks? Remember car dealerships that looked like ghost towns, all because of a tiny microchip the size of a fingernail, made in a single factory on the other side of the planet? We all felt it. We all saw how fragile the system had become. For 50 years the logic was simple: find the cheapest place on Earth to make something and make it there. We built a global system of incredible complexity, a delicate web of container ships, cargo planes, and just-in-time logistics. It gave us cheap t-shirts and affordable electronics, but it came at a monumental cost. We hollowed out our industrial heartland. We surrendered control of critical goods, from life-saving medicines to the chips that run our entire world. And we built our entire way of life on a supply chain that we discovered was a house of cards, ready to collapse at the first gust of wind. That wasn't a fluke. That was a warning. A deafening siren telling us that the fundamental model of American manufacturing was broken. But while that old system was cracking, a new one was being forged. Quietly, in labs and advanced factories across the country, a different idea was taking hold. For over a century, the way we made almost everything was subtractive. You start with a big block of material, a chunk of steel, a slab of aluminum, and you cut, drill, and grind away everything you don't need until you're left with the final part. It's incredibly wasteful. Sometimes over 90% of the raw material ends up as scrap on the factory floor. It's a process that requires massive, expensive, specialized machines, which is a big reason why manufacturing moved to countries with lower costs. This new way is the exact opposite. It's called additive manufacturing, but you know it as 3D printing. And you need to get the image of a little plastic desktop printer making keychains out of your head. That's like comparing a paper airplane to an F-35 fighter jet. We are talking about industrial-grade machines the size of a room, using high-powered lasers to build parts out of powdered titanium, one impossibly thin layer at a time. We're talking about printers that extrude advanced carbon fiber composites to create structures lighter and stronger than steel. We're talking about a world where complexity is free. In the old world, the more complex a part was, the more expensive it was to make. In the world of 3D printing, a simple solid cube costs the same to print as an intricate, hollow, honeycombed lattice of the same size. This simple fact completely upends 100 years of design and engineering logic. It allows American companies to create things that were literally impossible to make before. Take General Electric. They used to make their fuel nozzles for their advanced jet engines out of 20 individual pieces that had to be painstakingly welded and brazed together by hand. It was a complex, labor-intensive process. Today, using 3D printing, they make that same fuel nozzle as one single continuous part. The new design is 25% lighter and 5 times more durable. It's a generational leap in performance that simply could not have been achieved with old-school manufacturing. And it's everywhere. In Detroit, Ford engineers are 3D printing prototype parts for new vehicles, allowing them to test and iterate on a design in a single day, a process that used to take months and cost hundreds of thousands of dollars in custom tooling. At NASA, scientists are perfecting the technology to 3D print rocket engine components and even entire habitats on the surface of the moon using lunar dust as the raw material. In the world of medicine, doctors are creating custom-fit surgical guides and patient-specific implants, like knee and hip replacements that are a perfect match for an individual's anatomy, drastically improving recovery times and patient outcomes. This is the revolution. It's not a distant futuristic dream. It is a present-day reality, and it is accelerating at a breathtaking pace. And here's the most important part for all of us. It fundamentally changes the economic equation that sent American manufacturing overseas in the first place. The old model was driven by labor costs. The new model is driven by technology, software, and skilled operators. When your factory's productivity is determined by the speed of a laser and the brilliance of your design engineers, the advantage of cheap overseas labor evaporates. A 3D printer in Ohio costs the same to run as one in Shanghai. Suddenly, the calculus changes. It makes more sense to build factories closer to your customers. It makes more sense to manufacture on demand, reducing waste and eliminating the need for massive warehouses full of inventory. It makes sense to bring manufacturing back to the United States. This isn't just about patriotism. It's about pure economic and strategic logic. We are witnessing the dawn of a new era. An era of localized, digital, and resilient manufacturing. The Rust Belt has the potential to become the new tech belt, powered not by smokestacks, but by server farms and laser arrays. But this transition won't be automatic. It represents a monumental upheaval of established industries and a complete rethinking of skills and careers. So, how did this happen? How did a niche technology, born in a small California lab in the 1980s, grow into the force that is now poised to reinvent the backbone of the American economy? And most critically, what does this revolution truly mean for your job, your community, and the economic future of the United States of America? To understand that, we have to go back to the beginning. The year is 1983. Ronald Reagan is in the White House. The final episode of M*A*S*H is captivating the nation, and in a small lab in California, a man named Chuck Hull is frustrated. He wasn't trying to start a revolution. He was just trying to do his job. Hull worked for a company that used UV lamps to cure or harden thin coatings of plastic onto tabletops and furniture. It was a routine process, but for engineers like him, there was a universal bottleneck, a source of endless delays and astronomical costs: the prototype. Imagine you're an automotive designer in the early 80s. You've just spent months painstakingly drawing a new part for a car engine. Now, you need to see if it actually fits. To do that, you need a physical model, a prototype. Your drawings are sent to a machine shop, where a highly skilled craftsman takes a solid block of metal or plastic and begins the slow, laborious process of cutting, drilling, and grinding away everything that isn't your part. This is called subtractive manufacturing. It's like a sculptor chipping away at a block of marble. It's an art form. It's also incredibly expensive and can take weeks, sometimes months. And if you discover your design has a tiny flaw, you have to start the entire process all over again. This was the problem that consumed Chuck Hull. He watched this agonizingly slow dance between design and reality and thought there had to be a better way. And one night, in a flash of insight that would change the course of manufacturing, he connected the two seemingly unrelated parts of his world: the UV lamps he used for curing tabletops and the frustrating process of making prototypes. What if, he wondered, instead of starting with a big block and cutting things away, you started with nothing and built something up? What if you could take a liquid plastic, a photopolymer that hardens when hit with UV light, and build an object, layer by impossibly thin layer? The idea was elegant in its simplicity. You could take a 3D design from a computer, Slice it into thousands of digital cross-sections, like a virtual CAT scan. Then, you could use a focused beam of UV light to trace the first cross-section onto the surface of a vat of liquid polymer. The light would instantly harden the liquid it touched, creating a solid first layer. Then, a platform would lower that solid layer just a fraction of a millimeter deeper into the vat, and the laser would trace the second layer on top of the first, fusing it together. Layer after layer after layer. Rising from the liquid goop like a phantom, a solid three-dimensional object would materialize, built from the bottom up. He called his invention stereolithography. We call it 3D printing. It was the polar opposite of a century of manufacturing wisdom. Not subtractive but additive. Not carving away but building up. In 1984, Chuck Hull filed his patent. In 1986, he co-founded his own company to commercialize the technology, a company you might have heard of, 3D Systems. And in 1987, they sold their very first machine, the SLA-1. It was a clunky refrigerator-sized machine that cost hundreds of thousands of dollars, but to the engineers and designers who first saw it work, it was pure magic. Suddenly, the timeline for creating a prototype collapsed. What once took 2 months of skilled labor could now be printed, unattended, over a weekend. A design could be emailed on a Friday afternoon, and by Monday morning, a physical part would be sitting on your desk. You could hold it. You could test its fit. You could find the flaws. The impact was immediate and profound, but it was also contained. For nearly 2 decades, this was the world of 3D printing. It was an exclusive club for the giants of industry, aerospace firms, automotive companies, and massive medical device manufacturers. The companies that could afford the 6-figure price tags for the machines and the expensive proprietary materials they required. 3D printing was a powerful tool for what became known as rapid prototyping, and it gave these corporations a significant competitive edge. They could innovate faster, iterate on designs more quickly, and bring products to market sooner than their rivals. But for the average person, the small business owner, the garage tinkerer, it was completely inaccessible. The technology was locked down tight by a fortress of patents. Chuck Hull's original patent, and dozens of others that followed from 3D Systems and their main competitor Stratasys, covered the core processes of additive manufacturing. This meant that for 20 years, only a handful of companies could legally build and sell these machines. This limited competition kept prices sky high and slowed the pace of innovation for the wider public. The revolution was happening, but it was happening behind the closed doors of corporate research and development labs. It was a quiet revolution, a secret weapon for the Fortune 500. The dream of a 3D printer in every workshop, or even every home, seemed like pure science fiction. The machines were too big, too expensive, and the materials were too limited. The sleeping giant of American manufacturing was stirring, but it was far from awake. It was an industry of incredible potential, held in a state of suspended animation by the very legal protections that allowed it to be born in the first place. A clock was ticking down on those foundational patents, and with every passing year, the day they would expire drew closer. Most of the world was oblivious. They saw manufacturing as something that happened overseas, in massive factories churning out millions of identical items. The idea of custom, on-demand production here in America seemed like a relic of a bygone era. They had no idea that the technology that could potentially rewrite that entire economic equation was humming away in the basements of companies like Ford and Boeing. They didn't know that the forces of a free market were about to be unleashed on this guarded technology. For 20 years, the revolution was contained. But then, in the late 2000s, a legal countdown timer that started back in the Reagan administration finally hit zero. And the entire world of manufacturing was about to be turned upside down. The first domino to fall wasn't a company or a new invention but a single expiring patent. It belonged to a Minnesota-based company called Stratasys, and it was the legal fortress protecting the most intuitive, most recognizable form of 3D printing in the world. Fused deposition modeling, or FDM. You know this one. It's the one you see in high school tech labs and YouTube time-lapse. A thin plastic filament like a weed whacker string is fed into a hot nozzle, melted and drawn layer by layer, like a robot drawing with hot glue, to build an object from the ground up. For 2 decades, if you wanted to do this legally and commercially, you had to go through Stratasys. Their machines were industrial workhorses, costing anywhere from tens of thousands to hundreds of thousands of dollars. They were locked away in the R&D labs of Fortune 500 companies, automakers, aerospace giants, and medical device firms. It was a powerful tool, but it was a tool for the elite. But in 2009, that all changed. The key patent expired. The legal dam that had held back a global flood of innovation for 20 years finally broke. And on the other side of that dam wasn't a competing corporation, but a radical, almost philosophical movement that had been quietly building strength in the shadows. It was called the RepRap Project. Started in England by a brilliant and idealistic engineering professor named Adrian Bowyer, RepRap stood for Replicating Rapid Prototyper. Its goal was nothing short of revolutionary. Bowyer didn't just want to build a 3D printer. He wanted to build a 3D printer that could print itself, a machine that could replicate. His vision was to create a sort of mechanical evolution, an open-source machine that anyone could build, and that could then create the parts for another machine, for a friend, for a neighbor, spreading the technology like a seed. This wasn't a business plan, it was a manifesto. The designs were posted online for free. A small, passionate community of hackers, makers, and academics from around the world began collaborating, improving the designs and sharing their breakthroughs. They were building these printers in their basements and garages, piecing them together with parts from hardware stores and electronics they ordered online. It was a chaotic, beautiful grassroots movement. They were proving that the power to create physical objects, the very essence of manufacturing, didn't have to belong to giant corporations. Could belong to everyone. But for the average American, this was still a step too far. Building a RepRap machine required a deep understanding of electronics, software, and mechanical engineering. It was a project for dedicated hobbyists. The revolution needed a bridge. It needed someone to take this powerful open-source idea and package it for the masses. That bridge was built in a workshop in Brooklyn, New York. In 2009, three friends, Bree Pettis, a former art teacher and video blogger, Adam Mayer and Zach Smith, saw the potential of the RepRap project. They were part of a new, burgeoning maker movement, a subculture of tech-savvy DIY enthusiasts. They founded a company with a catchy, futuristic name, MakerBot Industries. Their first product, the Cupcake CNC, wasn't a sleek, finished product. It was a kit, a box of laser-cut plywood, nuts, bolts, wires, and circuit boards that you had to assemble yourself. It was challenging, it was finicky, but it worked. And it cost less than $1,000. For the first time, a regular person, a student, an artist, an entrepreneur could own a 3D printer. They took the open-source spirit of RepRap and combined it with the classic American startup ethos. They created a community, a website called Thingiverse, where users could upload and share their 3D designs for free. Suddenly, you didn't need to be a CAD expert to print something amazing. You could download a file for a replacement part for your dishwasher, a custom phone case, or a toy for your kid, and print it in your own home. The impact was immediate and explosive. MakerBot became the face of the consumer 3D printing boom. They were the Apple of the new movement, turning a complex piece of technology into something aspirational and accessible. The price of 3D printing didn't just fall. It plummeted off a cliff. Think about this. In 2005, a basic professional FDM printer from Stratasys might cost you $50,000. By 2011, you could buy a fully assembled MakerBot replicator for under $2,000. That's a price drop of over 95% in just a few years. This economic shockwave completely changed the landscape. Dozens, then hundreds of competitors sprang up around the world, most of them leveraging the same open-source designs. Companies in the US, Europe, and Asia started selling their own kits, their own fully assembled printers, pushing prices even lower. The technology that was once the exclusive domain of aerospace engineers was now being sold on Amazon. This democratization did something fundamentally important for American manufacturing. It wasn't about replacing factories overnight. It was about education and inspiration on a massive scale. For 2 generations, manufacturing in the United States had been something that happened somewhere else, in a giant, anonymous building you never went inside. Making physical things was seen as a low-skill job of the past. But suddenly, a new generation of Americans had direct, hands-on access to the tools of digital fabrication. High school robotics clubs were printing custom parts for their robots. Architecture students were printing complex models of their building designs instead of painstakingly building them from foam core. Entrepreneurs were prototyping new inventions on their kitchen tables, able to go from an idea to a physical object in a matter of hours, not weeks or months. This created a nationwide, decentralized talent pipeline. It was a grassroots training program for the next industrial revolution. Millions of young people were learning the language of 3D modeling and digital manufacturing, not because they had to in a class, but because it was fun. They were developing an intuitive understanding of design constraints, material properties, and the entire digital to physical workflow. This was the real revolution. It wasn't just about the printers themselves. It was about the people using them. It was the same pattern we saw with the personal computer in the 1980s. The Apple II and the Commodore 64 didn't immediately put IBM out of business. But they did create a generation of kids who grew up with computers, who learned to code in their bedrooms, and who went on to found the software companies that would define the next 30 years of the global economy. The hobbyist 3D printer was doing the exact same thing for manufacturing. It was seeding the future. It was training an army of innovators, designers, and problem solvers. And while the media was focused on people printing plastic trinkets and Yoda heads, something much more profound was happening in the background. These toys were getting more and more powerful. The materials were getting stronger. The software was getting smarter. And the people who had learned to use them in their garages and dorm rooms were now starting to graduate and get jobs at some of the most important companies in America. The line between hobbyist and professional began to blur. And the tools that were born in a movement of open-source sharing were about to be put to work in the most demanding, high-stakes environments imaginable, solving problems that had been unsolvable for decades. And one of the first and most spectacular of those problems was hidden deep inside the heart of a jet engine. For decades, engineers at companies like General Electric faced a brutal trade-off. To make an engine more powerful and more fuel-efficient, you needed to make it run hotter. But running it hotter put immense stress on the components. The components that controlled the fuel flow, the fuel nozzles, were especially vulnerable. A traditional fuel nozzle tip was a marvel of intricate engineering, but it was also an assembly of about 20 different tiny pieces, all painstakingly welded and brazed together by hand. It was a process with a high failure rate, and the final product, while functional, was a compromise. It was heavy, and its internal channels for mixing fuel and air were constrained by the simple fact that you had to be able to physically assemble them. You couldn't create the perfect, swirling organic pathways that fluid dynamic simulations said were ideal. The ideal shape was simply unmanufacturable. This single component was a bottleneck, holding back the potential of an entire generation of aircraft. GE's engineers, working on their next-generation engine, the LEAP, knew they had to do better. They needed a nozzle that was stronger, lighter, and far more complex internally than anything they could weld together. They needed to build the impossible. And so they turned to one of those super-powered industrial-grade versions of the desktop printers we talked about. A machine that didn't use plastic filament, but a fine metallic powder, a cobalt chromium alloy, a process called direct metal laser sintering. Imagine a flatbed covered in a layer of this metal powder, thinner than a human hair. A powerful laser, guided by a 3D computer model, zaps the powder, precisely tracing the first cross-section of the fuel nozzle. In that instant, the metal particles are fused, welded into a solid layer. Then a roller pushes a new, fresh layer of powder over the top, and the laser goes to work again, tracing the next cross-section and fusing it to the one below. Layer by layer, hundreds of thousands of times, the machine builds the fuel nozzle from the ground up. What emerged from that bed of powder was revolutionary. It wasn't an assembly of 20 parts. It was one single solid piece. A single, unified component that was 5 times stronger than its predecessor. Because there were no welds or brazing points to fail, its durability went through the roof. And because it was built layer by layer, the engineers could finally design those impossible internal channels. They used sophisticated software to create intricate, twisting, cooling pathways that mimicked the efficiency of natural structures, like the veins in a leaf or the structure of bone. The final product was 25% lighter, but its performance was off the charts. This wasn't just a better part, it was a paradigm shift. That one 3D printed nozzle unlocked a new level of performance for the entire LEAP engine, making it one of the most successful and fuel-efficient engines in aviation history. Today, every single one of those engines, powering hundreds of Boeing and Airbus jets across America and the world, has 19 of these 3D printed fuel nozzles inside. General Electric has now printed well over 100,000 of them. This wasn't a prototype or an experiment anymore. This was additive manufacturing, born from the open-source community, now operating at the heart of American industrial might, in one of the most demanding and regulated industries on Earth. This breakthrough sent a shockwave through the manufacturing world. If you could print a critical jet engine part, what else could you print? The answer came not from the skies, but from inside the human body itself. For surgeons, especially in fields like oncology and trauma, they faced a similar problem to the GE engineers: the tyranny of standard parts. When removing a cancerous tumor from a patient's jaw, for instance, a large section of bone might have to be taken out. The reconstruction often involved taking bone from another part of the body, like the leg, and trying to shape it to fit. It was an imperfect, often painful process. Alternatively, they could use a standard-sized metal plate or implant. But every human body is unique. A standard-sized implant is always a compromise, never a perfect fit. This could lead to longer, more complex surgeries, increased risk of infection, and suboptimal outcomes for the patient. What if you could give a surgeon an implant that was a perfect one-to-one match for the patient's own anatomy? This is where 3D printing became not just a manufacturing tool, but a medical miracle. The process is breathtaking in its elegance. It starts with a CT scan of the patient. That scan is converted into a highly precise 3D digital model of their skull, their hip, their knee, whatever needs repair. A biomedical engineer can then use that model to digitally design a custom implant that fits with sub-millimeter accuracy. It's not just a plate. It's a perfect mirror image of the bone that was lost, complete with a porous, lattice-like surface designed to encourage the patient's own bone cells to grow into it, making the implant a permanent part of their body. This digital file is then sent to a medical-grade 3D printer, which uses an electron beam or a laser to fuse layers of titanium powder, building that custom implant, atom by atom. Within days, a surgeon can hold in their hand a sterile, perfectly tailored piece of titanium that will only fit one person on the entire planet. The impact of this is profound. Case studies from medical centers across the country show how these patient-specific implants are changing lives. Surgeries that once took 8 to 10 hours can now be done in half the time, because the surgeon isn't wasting precious minutes in the operating room trying to bend and shape a generic plate to fit. Just clicks into place. Recovery times can be faster. The functional and aesthetic outcomes for patients are often dramatically better. We're talking about someone who has suffered a catastrophic facial injury in a car accident, or a patient who has lost part of their skull to cancer, being given a solution that restores not just function, but their own appearance, their own identity. This is the power of complexity on demand. Both the jet engine nozzle and the custom medical implant are objects that are incredibly complex, but that complexity is now essentially free. It takes the printer no more time or effort to create a twisting internal lattice structure than it does to create a solid block. This shatters a fundamental rule of traditional manufacturing, where complexity always equals cost. Suddenly, American engineers and doctors were given a new toolkit, a way to design things based on ideal performance, not on the limitations of the factory or the milling machine. They could now build with the same complexity and efficiency as nature itself. These high-stakes applications in aerospace and medicine were the ultimate proof of concept. They demonstrated that 3D printing wasn't just for plastic trinkets in a garage. It was a serious, robust technology capable of performing under the most extreme pressures imaginable, whether at 30,000 feet in the air or fused to human bone. And with that proof, the floodgates were about to open. The question was no longer if this technology would change American manufacturing, but how fast and how far it could spread. To answer that question, you have to look away from the gleaming billion-dollar research facilities of General Electric and the sterile clean rooms of medical implant manufacturers. The next phase of this revolution wasn't happening in the boardrooms of the Fortune 500. It was happening in garages in California, in small workshops in Texas, and in co-working spaces in Brooklyn. It was a quiet, grassroots insurgency powered not by massive government contracts, but by the expiration of a single crucial patent. For 20 years, the core technology behind the most common type of 3D printing, a process called fused deposition modeling, had been locked down. Think of it like this. It was as if one company owned the exclusive rights to the inkjet printer. They could set the price, control the market, and keep the technology exclusively in the hands of those who could afford machines that cost tens, or even hundreds of thousands of dollars. But in 2009, that patent expired. And in the world of technology, an expiring patent is like a dam breaking. Suddenly, an army of engineers, hobbyists, and entrepreneurs, who had been watching from the sidelines, were free to experiment, to innovate, to build their own versions of the technology. The result was an explosion of creativity and competition. The RepRap project, an open-source initiative, created a printer that could print its own parts, a self-replicating machine that spread the technology like a digital seed. Then came companies like MakerBot, which took these complex ideas and packaged them into a user-friendly box that could sit on your desk. This was the personal computer moment for manufacturing. The power of the factory, once the exclusive domain of industrial giants, was being miniaturized, democratized, and delivered to the American people for the price of a new laptop. And what did people do with this newfound power? they started solving problems. Take a look at Voodoo Manufacturing, a company started in a small Brooklyn workshop. They didn't have one giant, expensive machine. They had a farm of hundreds of small, inexpensive desktop 3D printers, all networked together. A customer could upload a design to their website, and their software would automatically dispatch the job to the next available printer. They were creating a factory that was flexible, scalable, and could produce one-of-a-kind items just as cheaply as it could produce 1,000. They printed everything from architectural models to promotional items to custom robot parts. They were proving that you didn't need a massive factory floor to be a manufacturer. You just needed a smart system and a few dozen small machines working in harmony. This model allowed for something that was previously a fantasy for most businesses: mass customization. Consider the case of a small company in Colorado that designs and sells specialized equipment for rock climbers. In the old world, if they wanted to produce a new carabiner or a unique piece of safety gear, they'd have to invest upwards of $50,000 in tooling and molds, and commit to producing 10,000 units all before they sold a single one. It was a massive gamble. But with 3D printing, they could design a new part in the morning, print a functional prototype in high-strength polymer by the afternoon, and have a professional climber testing it on a rock face by the weekend. They could make 10 different versions, get feedback, and find the perfect design without ever spending a dime on tooling. Better yet, they could offer custom-sized grips or personalized components, creating a product that was literally made for the individual customer. The barrier to entry for creating a physical product had just crumbled. This wasn't just about making new things, it was about changing how we make old things. It was about bringing manufacturing home. For decades, the logic was simple. If you wanted to make something cheaply, you made it in Asia. But that came with a price. 6-month lead times, communication barriers, the risk of intellectual property theft, and a complete inability to respond quickly to changes in the market. Now, picture a mid-sized company in Michigan that makes replacement parts for classic American cars. Their customers are restorers and hobbyists who need a specific, obscure plastic knob or a piece of interior trim for a 1967 Mustang, parts that haven't been mass-produced in 50 years. Previously, their only option was to find an original, painstakingly create a mold from it, and do a huge production run, leaving them with a warehouse full of parts they might not sell for years. It was slow and incredibly capital-intensive. Then they bought their first industrial-grade 3D printer. Now, when a customer in Arizona needs that specific dashboard knob, the company doesn't go to a warehouse shelf. They go to a digital file. They pull up the design, send it to the printer, and within a few hours, a perfect, durable replica is created using a material that's even stronger than the original. They can email the part file to a partner print shop in California and have it produced even closer to the customer. The part is made on demand. No warehouse, no minimum order, no wasted inventory. The cost of storing 1 million parts is reduced to the cost of storing a single hard drive. This is the death of scarcity. For the first time, a small American company could offer a virtually infinite catalog of products, produced locally and delivered in days, not months. They were now competing with overseas factories not just on quality and speed, but on pure agility. This shift created an entirely new class of entrepreneur. The inventor tinkering in their garage suddenly had a direct path to market. Think about the countless brilliant ideas that died on the vine because the inventor couldn't raise the $250,000 needed for traditional manufacturing. 3D printing became their launchpad. They could go from a sketch on a napkin to a 3D model on a computer, to a physical prototype in their hand in a single day. They could launch a Kickstarter campaign with a video of a working product, not just a drawing. They could take pre-orders and then print the first batch of their product themselves, in their own home or workshop. This is exactly what happened with companies producing everything from innovative smartphone cases to custom-fit headphones to modular robotics kits for kids. They weren't just designing a product. They were designing a new kind of business, one that was lean, adaptable, and deeply connected to its customers. They could incorporate feedback from one batch of customers directly into the design of the next, iterating and improving their product in real time. It was a manufacturing process that behaved less like a rigid assembly line and more like a living, evolving organism. What all these stories, the printer farm in Brooklyn, the classic car parts supplier in Michigan, the Kickstarter entrepreneur in a garage, were pointing to was a seismic shift in the landscape of American industry. It's a concept called distributed manufacturing. The idea is simple but profound. Instead of concentrating all production in a few massive centralized factories, you distribute it across a vast network of smaller, localized, digitally connected facilities. It's the same transformation that happened with information. A century ago, if you wanted to publish a message for the nation, you needed to own a newspaper or a broadcast tower. Today, anyone with a smartphone can reach the world. The same thing was now happening to physical objects. The power to create was being decentralized. This wasn't just about a new tool. It was about a new economic and logistical framework, one where manufacturing could be as agile, responsive, and customized as software. But this grassroots revolution, powerful as it was still largely happening at the scale of plastics, prototypes, and small batch production. The giants of industry, who had pioneered the high-end metal printing for jet engines and medical implants, were watching. They saw the speed and innovation bubbling up from below, and they began to ask a very different and much bigger question. What if you could take the agility of a desktop printer and combine it with the strength of industrial steel? What happens when this distributed model isn't just for small parts, but for the fundamental building blocks of our entire industrial world? What happens when the garage grows up? What happens is a revolution not of plastic trinkets, but of titanium, of superalloys, of the very materials that hold our world together. The garage doesn't just grow up. It plugs into a grid, a digital network that transforms the very definition of a factory. The factory is no longer a single sprawling building in one city. It becomes a decentralized, intelligent network of production cells, scattered across the country, all working in concert. This is the world of distributed manufacturing, and it's not a future tense concept. It's happening right now. Imagine this scenario. A critical U.S. Air Force transport plane, a C-17 Globemaster, is grounded in a remote location. A single complex hydraulic bracket deep inside the landing gear has failed. It's an old plane, and the part is no longer mass-produced. Under the old system, the logistics are a nightmare. Engineers would have to find the original blueprints, if they still exist in a usable format, send them to a specialized foundry, create a custom mold, cast the part, machine it to final specifications, test it, and then ship it halfway around the world. The entire process could take weeks, even months. The entire time, a strategic asset worth over $200 million, is nothing more than a very expensive paperweight. Now enter the new reality. An engineer on site takes a 3D scan of the broken part, or simply pulls up its digital file from a central database. This file, the digital DNA of the component, isn't sent to a foundry. It's uploaded to a secure cloud network. Within minutes, that file is analyzed and assigned to a production cell. But this cell isn't a massive factory. It's a small, highly automated facility outside of, say, Cleveland, Ohio. Inside this facility sits a machine the size of 2 refrigerators. This is a direct metal laser sintering, or DMLS, printer. Instead of squirting melted plastic, a DMLS machine uses a high-powered laser to draw on a bed of fine metal powder, in this case a high-strength titanium alloy. With each pass, the laser microwelds the powder into a solid layer, just 20 to 40 microns thick, thinner than a human hair. Then, a fresh layer of powder is spread, and the process repeats thousands upon thousands of times. For the next 30 hours, inside a sealed chamber of inert argon gas, the laser dances across the powder bed, growing the complex bracket from the bottom up, layer by microscopic layer. There are no molds, no cutting tools, no wasted material. The machine is building only what is needed, molecule by molecule. When it's finished, the part is excavated from the surrounding powder like a technological fossil, heat-treated to strengthen its molecular structure, and then finished to precise tolerances. The entire process, from digital file upload to a ready-to-ship, flight-certified titanium component, takes less than 3 days. The part is then flown directly to the grounded aircraft, which is back in service in a fraction of the time, at a fraction of the cost. This isn't science fiction. This is the power of the grown-up garage. Companies like Velo 3D, Markforged, and a network of service bureaus across the nation are building the infrastructure for this new industrial age. They're not just printing brackets. They're printing rocket engine components for companies like SpaceX and Relativity Space. Parts that are lighter, stronger, and contain intricate internal cooling channels that are physically impossible to create with any other method. This complexity is free aspect of 3D printing is a game changer. In traditional manufacturing, more complex parts are exponentially more expensive to make. With additive manufacturing, a simple solid cube costs roughly the same to print as a hollow, intricate lattice structure of the same size. This frees engineers to design for optimal function, not for the limitations of old-world manufacturing. They can use generative design software, where an AI algorithm helps design the strongest possible part with the least amount of material, resulting in bizarre, organic-looking structures that are perfectly optimized for their task. And this revolution extends far beyond the skies. In the medical field, it's becoming deeply personal. Imagine a patient who has been in a severe car accident, with part of their skull shattered. In the past, surgeons would use a generic metal plate, bending it by hand to approximate the right shape. Today, they can take a CT scan of the patient's head, convert it into a 3D model, and print a custom cranial implant made of biocompatible titanium. This implant fits the patient's unique anatomy with sub-millimeter precision. The same is true for spinal fusion cages, custom hip replacements, and surgical guides that show a doctor precisely where to cut and drill. We're moving from mass production to mass personalization, creating better outcomes and faster recoveries. In the automotive world, it's about speed and legacy. When a company like Ford or GM is developing a new engine, they can now 3D print a prototype block or cylinder head in a matter of days to test its performance. This allows for rapid iteration, shaving months off development cycles. For car enthusiasts, the holy grail is the ability to recreate parts that have been out of production for decades. Need a water pump housing for a 1968 Shelby GT500? Good luck finding one. But soon, you'll be able to simply download a certified digital file and have it printed in high-strength aluminum, keeping these classic machines on the road. What connects all these examples, aerospace, medical, automotive, is a profound shift. The factory is becoming defined by software, not just by its physical location. The value is migrating from the machine itself to the digital file, the digital twin of the physical object. This creates what's known as the software-defined factory. The network of 3D printers across the country becomes like a physical version of the cloud. Just as Amazon Web Services allows a startup to rent massive computing power without owning a single server, this new manufacturing network allows an inventor or a company to access millions of dollars of industrial printing capability on demand. This model fundamentally rewires the logic of supply chains. The fragility of our global supply lines was laid bare in recent years. A single factory shutdown or a single ship stuck in a canal can cause cascading shortages around the world. The distributed model offers a powerful antidote: resilience. If that facility in Cleveland gets hit by a blizzard, the network software simply reroutes the Air Force bracket job to an identical machine in Phoenix, Arizona, or Charleston, South Carolina. The system barely skips a beat. Production is no longer concentrated in one vulnerable location. It's spread across a robust, redundant, and domestic network. Of course, this isn't a silver bullet for all of manufacturing. For producing 10 million identical plastic bottle caps, traditional injection molding is still vastly cheaper and faster. The challenge of quality control across a distributed network is also immense. Ensuring that a part printed in Arizona is absolutely identical in every metallurgical property to one printed in North Carolina requires an incredible amount of process monitoring, data analysis, and standardization. For flight-critical or medical implant-grade parts, the certification process is justifiably rigorous and expensive, but the trend is undeniable. The technology is moving relentlessly up the value chain, from simple prototypes to functional, end-use parts in the most demanding industries on Earth. We are witnessing the early days of a manufacturing paradigm that is more agile, more customizable, and more resilient than anything that came before it. It's a system that brings production closer to the point of need, reducing shipping costs and environmental impact. It's creating a new class of high-skilled American jobs, not on the assembly line, but in operating these advanced machines, developing the software that runs them, and engineering the next generation of impossible-to-make parts. We've seen how this technology rebuilds parts, but what happens when it starts to rebuild entire industries and challenge the global economic order? What does a world look like where the most valuable shipping container is an email with an attachment? That question isn't just a clever thought experiment. It's the blueprint for the largest supply chain disruption in a century. For generations, the global economy has been built on a simple, brutal logic. Make things where it's cheapest, and then spend a fortune in time, fuel, and logistics to move them where they're needed. It was an equation that hollowed out American factories and built entire cities on the other side of the world. It's the reason the device you're watching this on likely traveled 10,000 miles overseas and land to get to you. 3D printing doesn't just offer a new answer to that equation. It rips up the paper and rewrites the laws of economic physics. The digital supply chain is the new reality. Instead of shipping a physical object, you ship the data, the design file, That data travels at the speed of light, for virtually no cost to any point on the globe. The physical object is then materialized or printed as close to the end user as possible. Think about the implications. A car company in Detroit can design a new side view mirror. In the old world, that design goes to a factory in Asia. Molds are created, 1 million units are produced, packed into shipping containers, loaded onto a massive vessel, and sent on a 3-week journey across the Pacific. They're unloaded, put on trains, then trucks, sent to a national distribution warehouse, then a regional one, and finally to a local auto parts store where it sits on a shelf waiting. In the new world, the designer in Detroit finalizes the file and emails it. It's sent not to one mega factory, but to 100 certified, smaller 3D printing hubs across the United States. A repair shop in Phoenix, Arizona, needs that mirror for a customer. They download the file, print the part on demand, and have it ready in a few hours. No container ship, no port congestion, no warehouse, no wasted inventory. The cost of international shipping, the risk of geopolitical disruption, the weeks of waiting, they all evaporate. This is the engine of a movement that economists have been debating for years. Reshoring, bringing manufacturing back to American soil. For decades, the primary driver of offshoring was the cost of labor. It was simply cheaper to pay someone overseas to assemble a product. But what happens when the primary laborer is a machine that prints a part from the ground up, with minimal human intervention? The labor cost advantage shrinks dramatically. Suddenly, the calculus changes. When labor is no longer the dominant factor, other things become more important. Speed to market, supply chain security, the ability to customize, and the cost of shipping. On all of those fronts, local, automated manufacturing wins. This doesn't mean the return of the giant, smog-belching factories of the 20th century. It means the rise of something far more agile and advanced: the microfactory. Imagine a network of clean, quiet, highly automated facilities, maybe no larger than a local supermarket, dotted across the country. One in rural Pennsylvania could specialize in printing aerospace-grade metal components. Another in central Florida could focus on patient-specific medical implants. A third, near a major agricultural hub in the Midwest, could be printing custom replacement parts for tractors and combines, eliminating the costly downtime that farmers face when a critical piece of equipment breaks during harvest season. This distributed model creates something our old supply chain desperately lacked: resilience. We all got a brutal lesson in the fragility of global logistics recently. A single ship gets stuck in a canal, and supply chains for everything from coffee to cars grind to a halt. A pandemic shuts down a single region, and the world runs out of critical components. The old model is a long, fragile chain. If one link breaks, the whole thing falls apart. A distributed network of microfactories is not a chain. It's a web. If one node goes down, the others can instantly pick up the slack. Production can be rerouted with an email, not a fleet of cargo ships. This isn't just an economic advantage. It's a matter of national security, ensuring that in a time of crisis, we can produce what we need, right here at home. Now, the inevitable and crucial question: what about jobs? The image of automation often conjures fears of a jobless future. And it's true, the repetitive manual assembly line jobs that define the old factory floor will not be coming back in the same way. But 3D printing isn't about replacing humans. It's about elevating them. It's creating a new class of manufacturing jobs, higher skilled, higher paid, and more creative. For every printer that's running, you need a technician who can maintain and repair that incredibly complex machine. You need materials scientists who are developing the next generation of printable alloys, polymers, and composites. You need digital designers and CAD specialists who can create and refine the 3D models, the digital blueprints of this new economy. You need quality control engineers who use advanced scanning technology to ensure that a printed jet engine turbine blade meets microscopic tolerances. You need software developers, logistics coordinators, and cybersecurity experts to manage this new digital supply web. These are not the jobs of the past. These are the high-tech, high-value jobs that can rebuild and redefine the American middle class for the 21st century. It's a shift from physical labor to intellectual labor. This new economic model also unlocks a phenomenon that was impossible with traditional mass production: the long tail of manufacturing. In the old world, a company had to be sure it could sell tens of thousands, if not millions, of an item to justify the massive upfront cost of tooling a factory. This meant that niche products, replacement parts for older models, and custom-designed goods were either prohibitively expensive or simply didn't exist. 3D printing flips that script entirely. The cost to print the first item is the same as the cost to print the 1,000th. This makes it economically viable to produce just one of something. Do you need a new battery cover for a 10-year-old digital camera? The manufacturer isn't stocking that anymore. But with a digital file, you can print one. Do you need a specialized ergonomic tool designed perfectly for your hand? You can have it. This opens up trillions of dollars in potential economic activity that was previously locked away. It allows businesses to serve incredibly niche markets at a profit. For consumers, it means a world where products are no longer just consumed, but co-created. A world where obsolescence becomes a choice, not a mandate. We are witnessing a fundamental inversion of the Industrial Revolution. For 200 years, we have been forced to conform to the products that factories could make. We all bought the same cars, the same phones, the same furniture because that was the only economical way. Now, for the first time, we are building a system where the products can conform to us. The factory is being reshaped to serve the individual, not the masses. The economic power is flowing away from massive, centralized corporations and being distributed across a decentralized network. The very geography of wealth and industry is being redrawn, moving from overseas ports to American towns. We've seen how it's changing the where and the how of manufacturing. But what about the who? What happens when this power to create, to turn a digital file into a physical reality, isn't just in the hands of corporations large or small, but in the hands of every single person? What happens when the factory isn't just in your town, but in your own home? That question isn't science fiction anymore. It's the reality unfolding in basements, garages, and home offices across the country. What happens is a fundamental shift in our relationship with the physical world. For over a century, the American consumer has been exactly that, a consumer. We buy, we use, we discard. The process of creation was a distant, almost magical thing that happened in a factory far away. 3D printing is severing that dynamic. It's creating a new class of individual, the prosumer, a hybrid of producer and consumer. Think about it. The dishwasher breaks. A tiny, insignificant plastic clip that holds the rack in place has snapped. In the old model, you have three frustrating options. 1. You spend hours online searching for the exact part number, pay $15 plus shipping for a 5-cent piece of plastic, and wait a week for it to arrive. 2. You call a repairman who charges you $100 just to walk in the door. Or 3. The most common American outcome, you give up and precariously balance your dishes for the next 5 years until you buy a whole new machine. The new model looks very different. You take out your phone, you scan the broken piece, or you find a file for it already uploaded by someone else with the same problem on a site like Printables or Thingiverse. You send the file to your 3D printer, and in 30 minutes, for the cost of about 12 cents in plastic, you have a brand new, perfectly functional part. You didn't just consume a solution. You produced it. You took control. This isn't just about convenience. It's a declaration of independence. It's the ultimate expression of the right to repair movement. For years, consumers have been fighting against companies that make their products intentionally difficult or impossible to fix, forcing us into their expensive repair networks or into buying new devices. They use proprietary screws, glue batteries in place, and refuse to sell replacement parts. 3D printing is the crowbar that pries open that closed ecosystem. It decentralizes repair. It takes power from a corporate headquarters and places it directly onto your kitchen counter. Farmers are already doing this, 3D printing discontinued parts for their John Deere tractors, refusing to be held hostage by a single supplier. This is a quiet, grassroots rebellion, fought not with picket signs, but with spools of filament. This empowerment extends far beyond simple repairs. It's creating entirely new microeconomies, a digital version of the classic American artisan. An engineer in Ohio can design a more aerodynamic mount for a drone camera, upload the file to a marketplace like Etsy or My Mini Factory, and sell that digital blueprint to people all over the world. His inventory is infinite. His manufacturing plant is a hard drive. His distribution network is the internet. He's not selling a physical object. He's selling an idea, a solution, that the buyer then materializes on their own terms. This is a profound change. The barrier to entry for becoming a creator of physical goods is no longer access to capital for a factory and a supply chain. The barrier is now imagination and skill. It's the democratization of invention. We're seeing custom tools designed for specific trades, personalized accessibility aids for people with disabilities, and educational models for students that would have been prohibitively expensive to produce traditionally. An artist in Portland can create intricate sculptures that exist only as data until someone in Florida decides to print one. It's a global market with a hyper-local factory. But this new frontier, like any frontier, is wild and untamed. And it brings with it a host of monumental challenges that our society is only just beginning to grapple with. The most significant is a looming crisis in intellectual property. Our entire system of patents, copyrights, and trademarks is built on the idea that it's difficult to copy a physical object. What happens when copying a physical object becomes as easy as copying an MP3 file? We all remember the music industry's war with Napster in the late 90s. It was a brutal, chaotic transition that fundamentally reshaped how we consume media. 3D printing is poised to be the Napster for everything else. If you can download a car, or at least the files to print its parts, what does that mean for the intellectual property of Ford or General Motors? If you can print a perfect replica of a Disney character, what does that mean for their copyright? The potential for piracy isn't just about lost revenue for a company. It becomes a question of safety and reliability. And that leads to the second great challenge, liability. In the traditional manufacturing model, if a part in your car fails and causes an accident, the chain of responsibility is clear. It lies with the manufacturer, the supplier, or the mechanic who installed it. Now consider a 3D printed world. If a brake caliper, downloaded from an open-source website and printed on a home machine with third-party filament, fails on the highway, who is at fault? Is it the original designer of the file, who may be an anonymous hobbyist in another country? Is it the website that hosted the file? The company that made the printer? The manufacturer of the plastic filament? Or is it the individual who printed and installed it? Our legal system is built for a world of clear-cut liabilities, not a decentralized network of creators and prosumers. We don't have a framework for this. There are no established standards for testing the structural integrity of a crowdsourced design printed on one of 1,000 different machines using countless variations of materials. This isn't just a legal puzzle. It's a massive public safety concern. Finally, there's the hurdle of the skills gap. While printers are becoming more user-friendly, the ability to design something complex and functional from scratch remains a specialized skill. Using computer-aided design or CAD software is not intuitive for most people. It requires training, practice, and a different way of thinking about objects in three-dimensional space. We can all download and print things others have made, but to truly unlock the potential of the home factory, we need a population that can not only operate the machine, but can also design the future it will print. It represents a need for a new kind of digital literacy, one that extends beyond the screen and into the physical world. We stand at a crossroads. In one direction lies a future of unprecedented individual empowerment, creativity, and sustainability, where we fix more and waste less, where innovation is decentralized, and where small creators can compete on a global scale. In the other direction lies a chaotic landscape of intellectual property theft, questionable safety standards, and a legal quagmire that could stifle the technology before it ever reaches its full potential. We've seen how this technology empowers the individual, but it also creates unprecedented challenges in law, safety, and economics. So how do we navigate this? How does America, as a nation, build the guardrails for this new industrial age without stifling the very innovation that makes it so powerful? The answer lies in education, policy, and a complete reimagining of what a Made in America product truly is. Let's start with education, because any revolution that isn't built on a foundation of knowledge is destined to crumble. The factory of tomorrow isn't just a place of sparks and steel. It's a hub of data and design. The skills that defined a generation of American workers, the intuitive feel for a lathe, the practiced eye of a welder, are not becoming obsolete. They are becoming the bedrock for a new hybrid skill set. The machinist of the 21st century is also a coder. The assembly line worker is also a data analyst, monitoring a fleet of autonomous printers for peak efficiency. This isn't a hypothetical future. It's happening right now in forward-thinking vocational schools and community colleges across the country. We need a national push to tear down the artificial wall between the workshop and the computer lab. The student learning computer-aided design, or CAD, should be just a few feet away from the student learning to calibrate a multi-material 3D printer. They need to understand that the digital file is not separate from the physical object. It is the physical object, waiting to be born. This requires a curriculum that's as agile as the technology it teaches, one that partners directly with local industries to train for the jobs that exist and the jobs that are just over the horizon. It's about fostering what's called digital literacy in the physical world. It's teaching a new generation that their creativity, their ability to solve a problem on a screen, can be translated into a tangible, functional part in a matter of hours. This fundamentally changes the appeal of manufacturing. It's no longer just about physical labor, it's about intellectual creation. It attracts a diverse new talent pool: coders, designers, artists, and gamers, who might never have considered a career in making things. This infusion of new blood, new perspectives, is the life force of innovation. And for the existing workforce, it's not about replacement. It's about empowerment. It's about providing accessible upskilling programs that give a veteran welder the tools to command a laser-sintering machine, transforming their years of hands-on experience with materials into an invaluable asset in the additive age. But education alone is a motor without a chassis. It needs a framework of smart, forward-thinking policy to guide it. When we talk about policy, the immediate fear is regulation that stifles growth. But the right kind of policy doesn't build walls, it paves roads. First and foremost is the monumental challenge of intellectual property. In the old world, stealing a design meant physically stealing blueprints. In the new world, it can be as simple as copying a file. How does a small American startup protect its breakthrough design from being instantly replicated on the other side of the world? We need to develop new international standards and enforcement mechanisms for digital design assets, treating them with the same seriousness as a patent for a chemical formula or a copyright for a piece of software. Then there's the issue of standards and certification. If a company 3D prints a critical bracket for an airplane, how do we guarantee it's as strong and reliable as a forged one? The FAA, the FDA, and other regulatory bodies are in a race against time to develop protocols for testing and validating additively manufactured parts. This isn't red tape, it's a trust-building exercise. Creating these clear, reliable standards gives large corporations the confidence to integrate 3D printing into their critical supply chains, and it gives consumers the confidence to fly in a plane or use a medical implant made with this technology. This government-led standardization creates a stable, predictable market where innovators can thrive. Furthermore, policy can act as a catalyst. Programs like America Makes, the National Additive Manufacturing Innovation Institute, show the power of public-private partnerships. By co-funding research, connecting startups with industrial giants, and creating a shared space for problem-solving, the government can de-risk innovation. It helps shoulder the enormous cost of early-stage research and development, allowing smaller, more agile companies to take chances they couldn't afford on their own. This isn't about picking winners and losers. It's about creating an entire ecosystem where more players have a chance to win. It's about tending the soil of American ingenuity so that 1,000 new ideas can bloom. This brings us to the most profound shift of all: reimagining what Made in America even means. For a century, that label conjured an image of a massive factory, a sprawling assembly line, a singular place where raw materials went in one end and a finished product came out the other. It was a label defined by geography and physical process. Additive manufacturing shatters that definition. Consider this. A prosthetic arm is designed by a team of engineers in California. The custom-fit software is coded in Texas. A new lightweight polymer for its construction is developed at a university in Massachusetts. The digital file is then sent to a small, on-demand 3D printing hub in rural Ohio, which prints the final product and delivers it to a patient in the same state. Where was that arm made? The answer is everywhere. And therefore it was made in America. The value is no longer concentrated in the final assembly. The value is in the design, the software, the material science, the intellectual property. The factory is now a distributed network of knowledge and creativity. The Made in America label is no longer just a stamp of origin. It's a stamp of innovation. This is a seismic shift. It means we can stop chasing the low-cost labor model that dominated the late 20th century. Our competitive advantage isn't the cost of our labor, it's the quality of our ideas. This new definition also brings manufacturing home, but not in the way we might imagine. It doesn't necessarily mean the return of the million-square-foot factory. It means the rise of 10,000 micro-factories. It means a small town in Nebraska can become a global hub for manufacturing specialized agricultural drone parts. It means a business in a strip mall in Florida can produce custom medical devices for local hospitals. It decouples manufacturing from massive capital investment and centralized labor pools. Democratizes production. This is the ultimate guardrail. By focusing on education, we create a workforce that can command the technology. By implementing smart policy, we create a safe and competitive marketplace. And by redefining Made in America around innovation, we play to our nation's greatest strength. We stop trying to win yesterday's game and start designing the rules for tomorrow's. We are building a system that is not just resilient to global shocks, but is inherently anti-fragile. A decentralized network of American ingenuity that is more adaptable, more creative, and more powerful than any centralized system could ever hope to be. We've laid out the blueprint for how to build this future. But what does that future actually look like when it's fully realized? What happens when every town can have its own factory, every entrepreneur can become a manufacturer, and the very concept of a global supply chain is turned on its head? The final revolution is not in the technology itself, but in what we, as a nation, choose to build with it. This choice forces us to look beyond just reshoring jobs. It compels us to redefine what a job in manufacturing even looks like. We are not just bringing the factory back to America. We are bringing a fundamentally new kind of factory. The factory floor of tomorrow is not a place of repetitive, manual labor, but a hub of creativity and technical expertise. The most valuable asset is no longer the strength of a worker's back, but the power of their imagination and their ability to translate a digital file into a physical reality. We're witnessing the birth of the digital craftsman, an individual who is part designer, part engineer, and part materials scientist. These aren't the low-skill jobs that left decades ago. These are high-skill, high-wage careers that require a blend of digital literacy and hands-on problem-solving. This shift represents a monumental opportunity to reskill the American workforce. Community colleges, trade schools, and universities are already beginning to develop curricula centered around additive manufacturing, creating a pipeline of talent ready to power this new industrial age. It's a chance to build a manufacturing sector that is more inclusive, more innovative, and more rewarding for the people who are its lifeblood. Instead of competing on who can perform a repetitive task the cheapest, we compete on who can design the most efficient part, who can develop the most advanced material, and who can solve the most complex problem. This is a race to the top, and it's a race America is uniquely positioned to win. But the revolution extends far beyond the factory walls. It fundamentally rewrites the rules of national security and supply chain resilience. For decades, we operated on a model of global efficiency, creating sprawling, intricate supply chains that stretched across oceans. While economically efficient in times of stability, recent history has shown us just how fragile that system is. A single pandemic, a blocked shipping canal, or a geopolitical flare-up can bring the flow of critical goods to a screeching halt, leaving us vulnerable. 3D printing offers a powerful antidote to this fragility. Imagine a future where the Department of Defense no longer needs to maintain massive, costly warehouses of spare parts for aging aircraft. Instead, they can have digital inventories, libraries of files that can be transmitted to a forward operating base, a naval vessel at sea, or a domestic depot and printed on demand. A critical bracket for a fighter jet that would have taken months to source can be fabricated in hours. This isn't science fiction. This is happening right now. It shrinks the supply chain from thousands of miles to a few feet. It transforms logistics from a vulnerability into a strategic advantage. During a national health crisis, instead of waiting for shipments of swabs or ventilator parts from overseas, a network of local 3D printers could be activated, producing millions of units within days. This is resilience. This is manufacturing sovereignty. It's the ability to make what we need where we need it precisely when we need it most. And this newfound power of localization and customization will transform our lives as consumers. We are standing on the precipice of an era of mass personalization. The concept of one size fits all is a relic of the mass production age. In the additive age, the product can be tailored to the person. Think of athletic shoes with midsoles 3D printed to the exact contour and pressure points of your foot, providing a level of comfort and performance previously reserved for elite athletes. Imagine going to a dealership, not to pick a car off the lot, but to customize interior components, the dashboard layout, the gear shift, the trim, all printed to your exact specifications and aesthetic tastes. This revolution is most profound in medicine. We've already seen custom surgical guides and dental implants, but the horizon is so much broader. Soon, doctors will be able to take a CT scan of a patient's broken bone and 3D print a titanium implant that is a perfect, unique match for their anatomy, promoting faster healing and better outcomes. The potential for bioprinting, using living cells as the ink, points toward a future where we could one day print replacement tissues and even organs, tailored to the individual to eliminate the risk of rejection. This is technology that doesn't just make our lives more convenient, It makes them better, healthier, and longer. Perhaps the most quintessentially American aspect of this revolution is its power to democratize manufacturing. The Industrial Revolution centralized power in the hands of those who could afford to build massive factories. The digital revolution through 3D printing does the exact opposite. It distributes it. An entrepreneur with a brilliant idea for a new product no longer needs to seek millions in venture capital to pay for expensive tooling and molds just to create a prototype. They can design it on a computer, print it overnight for a few $100s, test it, and iterate on the design the very next day. This radically lowers the barrier to entry for innovation. The garage is once again the American factory floor. A small business in rural Ohio can now compete with a multinational corporation, not by trying to match their scale, but by outmaneuvering them with speed, creativity, and the ability to serve niche markets with custom products. This fosters a Cambrian explosion of entrepreneurship, creating new businesses, new wealth, and new opportunities in communities that have been left behind by globalization. It empowers individuals to become creators, producers, and manufacturers, turning the American spirit of ingenuity into tangible, market-ready products. Now it's crucial to be realistic. This transition is not without its challenges. The science of materials is still evolving. We need a wider palette of printable substances with proven reliability and strength. Quality control and standardization at a massive scale remain significant hurdles. How do you certify that a 3D printed aircraft part made in Alabama is identical to one made in California? And the issue of intellectual property is a complex digital minefield. When a physical object is just a data file, how do we protect designs from piracy and ensure creators are compensated? These are not trivial problems, and they will require a concerted effort from industry, academia, and government to solve. We need to invest in education, establish new standards, and create a legal framework for this new age. But these challenges should not be seen as roadblocks. They should be seen as the next frontier of innovation. They are the problems that the next generation of American engineers, lawyers, and entrepreneurs will solve. Because what we are talking about is not a simple upgrade to our existing manufacturing infrastructure. It is a fundamental paradigm shift. It is the third industrial revolution. The first was built on steam and iron. The second, on the assembly line and electricity. This third revolution is built on data, computation, and the ability to turn digital bits directly into physical atoms. We stand at a pivotal moment in American history. We have been given a tool that allows us to rethink not just how we make things, but where we make them, who makes them, and what it means to be a manufacturing nation in the 21st century. This is our chance to build a future that is more resilient, more innovative, more personalized, and more equitable. It's an opportunity to create an economy where manufacturing is not a memory of a bygone era, but the vibrant, beating heart of our future prosperity. The revolution is here. The printers are humming. The only question left is the one we started with. What will we, as a nation, choose to build with it?